Hi, a very long time ago, before I was born, even when the universe doesn't existed, when it was extremely small and dense, these quantum fluctuations, in quantum physics, a quantum fluctuation is a temporary random change in the amount of energy in a point in space as prescribed by this guy. Okay, so these quantum fluctuations could have been amplified by the extreme conditions of the Big Bang. Some theories propose that these quantum fluctuations were responsible for triggering the inflationary period, a rapid exponential expansion of the universe in the early moments after the Big Bang. As the universe continued to cool and expand, matter began to coalesce under the influence of gravity, giving rise to the first generation of stars and galaxies. Over millions of years, these cosmic furnaces ignited, forging heavier elements through nucleosynthesis and seeding the cosmos with the raw materials necessary for formation of planets, moons, and ultimately life itself. When a star dies, collapsing under their own weight to form the black hole or exploding in cataclysmic supernova, scattering heavy elements into the interstellar medium, the building blocks of life such as carbon, oxygen, and nitrogen were synthesized and dispersed throughout the cosmos. Meanwhile, galaxies danced in the gravitational ballads, merging and colliding over cosmic timescales, giving rise to colossal structures like galaxy clusters and superclusters. While this large-scale distribution of matter in the universe called the cosmic web, the universe in its baby stages was hot and dense. Approximately 380,000 years after the Big Bang, the universe cooled sufficiently for the electrons to hug with protons, forming neutral hydrogen atoms. This important movement, called recombination, is when the universe changed from being filled with a hot gas called plasma to being filled with neutral atoms. Photons, which were previously scattering off free electrons, suddenly gain the freedom to travel unimpeded. These primordial photons released during recombination constitute the cosmic microwave background radiation. The cosmic microwave background is leftover radiation from the Big Bang or the time when the universe began. The largest gravitationally bound structures in the universe are called galactic clusters. They are immense collection of galaxies, hot gases, and dark matter, all held together by their mutual gravitational attraction. Galaxies are individual star systems within the cluster. They range in size, shape, and type from spiral and elliptical galaxies to irregular ones. The hot, diffused gas that fills the space between galaxies in the cluster called the intracluster medium. The intracluster medium is primarily composed of ionized hydrogen and helium along with the other trace elements. It emits X-rays due to its high temperature, which can exceed tens of millions of degrees Celsius. Then there are these vast regions of space characterized by extremely low matter density compared to the average density of the universe, called the cosmic voids. They represent the opposite of what we typically associate with cosmic structures like galaxies, clusters, and filaments. Voids are largely empty spaces spanning tens of millions to hundreds of millions of light years across. Despite their low matter density, cosmic voids are not entirely empty. They still contain some matter, including dark matter and sparse galaxies, but the density is significantly lower compared to the surrounding regions. One intriguing aspect of cosmic void is their effect on the motion of galaxies. Galaxies within the voids experience relatively weak gravitational forces compared to those in the denser region. As a result, they tend to move away from the void center, leading to what's known as the void inflow phenomena. Then there is this hypothetical form of matter which is about 27% of the mass of the universe. It does not emit, observe, or reflect electromagnetic radiations. Hence, it is invisible and fundamentally different from the matter what we are familiar with. Wait a minute. If it is invisible, then how it was observed? First, it's hypothetical, and the second is that despite being invisible, its presence is inferred through its gravitational effects on the visible matter. So, to understand that, first we have to understand this. Gravitational lensing is a phenomenon predicted by Einstein's theory of general relativity, which describes how mass curves the fabric of space-time. This curvature of space-time affects the path of the light traveling through it, causing it to bend around massive objects. When light from a distant source passes near one of these massive objects, its path is altered by the curvature of space-time, causing the light rays to converge or diverge. This occurs when the gravitational field of the massive object is strong enough to significantly distort and magnify the light from a background source. Strong lensing can produce dramatic effects such as Einstein rings, when the light from a distant object is bent into a complete circle around the lensing object. Anyways, gravitational lensing occurs when the gravitational field of the dark matter bends and distorts light from a distant object, revealing its presence indirectly. Dark matter is theorized to be composed of non-baryonic particles, meaning that they are not made up of protons and neutrons like ordinary matter. Dark matter particles interact extremely weakly with regular matter, making them extremely difficult to detect directly. One more question. How universe is expanding? The existence of a mysterious form of energy was inferred from observations of distant supernova in the late 1990s, which revealed that the expansion of the universe is not only ongoing but accelerating over time. The dark energy is around 68% part of the universe, drives the accelerated expansion of the universe. But if the universe is infinitesimally large, how do we know that if the universe is expanding? When an object moving away from an observer emits electromagnetic radiation such as light with its wavelength stretched, this elongation of wavelength results in a shift of observed light toward the longer wavelength end of the electromagnetic spectrum. In terms of visible light, this shift manifests as a shift toward the red end of the spectrum. In astrophysics, redshift is primarily observed in the spectra of galaxies. The expansion of universe as described by the Big Bang theory causes galaxies to move away from each other. As a result, the light emitted by these galaxies undergoes redshift due to the expansion of the space between them and the observer. Conversely, blue shift occurs when an object is moving toward an observer. Blue shift can be observed in various astronomical phenomena such as when the stars or galaxies are moved toward the Earth. Now, at the core of a massive star, nuclear fusion reactions typically sustain the star against the inward pull of the gravity. These reactions convert lighter elements such as hydrogen and helium into heavier elements through a series of fusion reactions. However, as the star ages and consumes its nuclear fuel, the balance between gravity's inward force and the outward pressure generated by fusion weakens. When the core's nuclear fuel is depleted, gravity takes over, causing the core to collapse rapidly. This collapse triggers a dramatic increase in temperature and pressure, leading to a rapid fusion of heavier elements. This sudden fusion process releases an enormous amount of energy, causing a tremendous explosion known as supernova. It represents the death of a star. A supernova explosion, leaving behind a dense core composed mostly of neutrons, hence the name neutron star. Neutron stars typically form within the milliseconds to seconds after a supernova explosion. During the explosion, the outer layers of the stars are expelled, leaving behind the extremely dense core as a neutron star. A type of neutron star that emits beams of electromagnetic radiation from its magnetic poles is called the pulsar. As the neutron star rotates, these beams sweep across space, appearing as pulses of radiation when observed from Earth. Pulsars are formed shortly after a neutron star is created during a supernova event. The intense magnetic fields of neutron stars are thought to play a crucial role in creating the beams of radiation emitted by the pulsar. When the core of a massive star collapses under its own gravity during a supernova explosion, if the core's mass exceeds a certain threshold known as the Chandrasekhar limit, about 3 solar masses, it collapses into a singularity, forming a black hole. This singularity is a point where the gravitational pull becomes infinite and spacetime itself is wrapped beyond recognition. It's essentially a breakdown of our understanding of the physics, which means if you think very hard about the black holes, you end up like this. Surrounding this singularity is the event horizon, a boundary beyond which nothing, seriously nothing, not even the information, can escape the gravitational pull of the black hole. Once an object crosses this threshold, it's drawn toward the singularity, leading to what's colloquially referred to as spaghettification, a process where the gravitational forces stretch and tear apart anything falling into the black hole. Supermassive black holes found at the center of the galaxy with masses millions to billions of times that of our sun. Time behaves differently near black holes due to their extreme gravitational fields. According to Einstein's theory of general relativity, time passes more slowly closer to a massive object. This means that if you were observing someone falling into a black hole from a safe distance, you would see them moving slower and slower as they approach the event horizon, eventually appearing frozen in time. The gravitational pull of these black holes is so immense that they attract surrounding gas and dust, forming an acceleration disk. A matter spiraled inwards toward the black hole, it becomes heated to extreme temperatures, emitting intense radiation across the electromagnetic spectrum. This process of acceleration is highly efficient at converting gravitational potential energy into radiation, resulting in the luminous emission characteristic of active galactic nuclei. And if this luminous emission is too high, then the AGN is called quasar. The luminosity of the quasar is mind-boggling, often outshining entire galaxies despite being confined to a relatively small region of space. Some of the most powerful quasars can emit thousands of times more energy than the entire Milky Way galaxy. According to the general relativity, massive objects like stars and planets curve the fabric of space-time, causing what we perceive as gravity. Wormhole take this curvature to an extreme, theoretically bending space-time so severely that it forms a bridge between two distant points. A wormhole is a theoretical tunnel-like structure that connects two separate points in space-time, potentially allowing for instantaneous travel between them. However, constructing and stabilizing a traversable wormhole pose immense challenges. One of the key obstacles is the requirement of exotic matter or energy with negative mass or negative energy. This exotic matter would need to counteract the gravitational forces that would otherwise collapse the wormhole. Despite being theoretically allowed by certain solutions of the equation of general relativity, the existence and properties of the exotic matter remains purely speculative and have not been observed in nature. Cosmic rays, which are high-energy particles originating from various astrophysical sources in the universe, these particles, which can be protons, electrons, or atomic nuclei, travel through space at extremely high speeds, often close to the speed of light. Unlike electromagnetic radiation like light or radio waves, cosmic rays are composed of matter particles, making them distinct in their interaction with other matter. The origins of the cosmic rays are diverse and include sources such as supernova explosion, active galactic nuclei, and even outside our galaxy, such as from the other galaxies, or perhaps from more exotic sources like gamma ray bursts. Cosmic rays have significant implications for various fields of science. They can influence atmospheric processes such as cloud formation and lightning, whereas gamma ray bursts are among the most energetic events in the universe, emitting more energy in a few seconds to a minute than the sun will emit in its entire lifetime. These bursts were discovered unexpectedly in the late 1960s by satellites designed to monitor nuclear tests on the Earth, which detected brief flashes of gamma rays coming from random random directions in the space. Long duration GRBs, when matter falls onto the black hole or neutron star, it releases a tremendous amount of energy in the form of gamma rays along two narrow jets that blast out from the poles of the collapsing star. These jets punch through the star's outer layers, producing the burst of the gamma rays we observe from Earth. Short-range GRBs, on the other hand, are thought to be produced by the merger of compact objects such as neutron stars or black holes. When these dense remnants of the dead star orbit around each other and eventually merge, they release a burst of energy in the form of gamma rays. Since gamma rays have high energy, they can travel vast distances through space without being significantly absorbed or scattered. This allows us to detect gamma ray bursts from objects that are billions of light years away, give us a glimpse into the universe's distant past. Asteroids are rocky objects that orbit around the Sun, mostly found in the asteroid belt between Mars and Jupiter. They vary in size from small boulders to several hundred kilometers in diameter. Asteroids are often considered remnants from the early formation of the solar system and are primarily composed of rock and metal. Comets, on the other hand, are icy bodies that orbit the Sun in highly elliptical orbits, often coming from outer regions of the solar system. They consist of a mixture of ice, dust, rocky particles, and organic compounds. When a comet approaches the Sun, its icy surface sublimates, creating a glowing coma and sometimes a tail that points away from the Sun due to solar wind and radiation pressure. Meteoroids are small, rocky, or metallic objects that travel through space. They can range in size from a grain of sand to several meters across. Meteoroids come from various sources, including fragments of asteroids or comets. When a meteoroid enters the Earth's atmosphere and burns up due to the friction with the air, it creates a streak of light called the meteor or shooting star. That's it. That is our universe. Show your support by hitting the like button so that I can talk about multiverse in next video. And for now, thanks.